Hello everyone, in this video we will be learning about linear approximations and Taylor polynomials. Let us start with linear approximations. So to start with, let's say we have this graph and we have a function f of x, and let's say this is our point A, and at the point A, the x value is A and the y value is f of A. So at point A we draw the tangent line. What we will do is that we will try to find the equation of the tangent line. So first of all, let's start with a reminder that if I want to find the slope of the tangent line at a point A, this is finding the derivative of the function f of x at the point A. So we compute the limit of f of a plus h minus f of a divided by h as h approaches 0. So again, this is the slope of the tangent line at the point A f of A. And now we would like to find the equation of the line, so not just the slope. The way to find an equation of a line, so the point slope form of the line, this is the form of the line that uses a slope and a point. So this is what the point slope form of a line means. It's how we write the equation of a line using a slope and a point. So the point slope form of a line is y minus y1 equals to m times x minus x1. As you might notice, m is the slope, x1, y1, this is a point. So now we already agreed above that the derivative at point A, so f prime of A, this is the slope, so we can write this instead of m. Also, we have a point A, f of A, we can write this instead of x1, y1. So now let's replace these two things in the equation of the line. So what do we get? As I said, so instead of m, we will write f prime of A, and instead of x1 we will write A, and instead of y1 we will write f of A. And then we will solve for y, so we move f of A to the other side. We get y equals to f of A plus f prime of A times x minus A. And this is a linear approximation near a point A f of A. This is how we approximate. So since we are saying linear approximation with an L, so we will call it L of x. So L of x equals to f of A plus f prime of A times x minus A. Now, just to point out that questions might either ask you to find the linearization of f of x near the point A f of A, or they might ask you for a linear approximation. These are all the same thing. So let's look at an example. Find the linear approximation of ln of x at x equals to 1 and use it to approximate ln of 1.1. So first, let's start with the first part of the question. Find the linear approximation of ln of x at x equals to 1. Let's do this. Okay, so since we are finding the linear approximation at x equals to 1, this means that a, in our above formula, a equals to 1. So first, let's rewrite the formula, what we got for L of x. L of x equals to f of a plus f prime of a times x minus a. And now we agreed that a is 1, so I can rewrite this as f of a plus f f of 1 plus f prime of 1 times x minus 1. Now what's left for me to do is to find f of 1 and f prime of 1. So let's find this on the side. If f of x equals to ln of x, so f of 1 equals to ln of 1. So I can write this, I can plug this in here, so I get ln of 1 here. And for f prime of 1, let's find this. Since f of x equals to ln of x, so the derivative of ln of x is 1 over x. Now let's plug in 1 derivative and we evaluate it at 1. So instead of the x, I can write 1. So this is 1 over 1, which is equal to 1. So let's write it here. So I get 1 times x minus 1. And if I write ln 1 on my calculator, this gives 0. So my final answer is x minus 1. This means that the linear approximation of ln of x at x equals to 1 is x minus 1. Now let's move on to the second part of the question. Let's approximate ln of 1.1. So here before we had ln of x. Instead of the x, I want a 1.1. All I have to do is find L of 1.1. This is equal to 1.1 minus 1, which is equal to 0.1. And this is my approximation of ln of 1.1. And we will now look at another example. So find the linear approximation of sine of x squared at x equals to 0 and use it to approximate sine of 0.01. So first of all, as usual, we write L of x, which is equal to f of a plus f prime of a times x minus a. Next, we know that x equals to 0, so a equals to 0. So we plug in a equals to 0 in here. So we get f of 0 plus f prime of 0 times x minus 0, which is x. Now let's find f of 0 and f prime of 0. So f of x equals to sine of x squared. Then f of 0 equals to sine of 0 squared, which is equal to sine of 0, which is 0. Next, f prime of x, don't forget that to find the derivative of sine of x squared, this is the chain rule. So first we find the derivative of what's outside, so the derivative of sine is cos. We evaluate it at what's inside, so evaluate the cos at x squared. And then we multiply it by the derivative of what's inside, so we multiply it by the derivative of x squared, which is 2x. And now we would like to evaluate this derivative at 0. So we get cos of 0 times 2 times 0, which is 0. So both of these terms are 0, therefore L of x is 0. Now we would like to use L of x to approximate sine of 0.01. Don't forget that above we have sine of x squared. In order to approximate sine of 0.01, I want x squared to be equal to 0.01, so x will be the square root of 0.01. So this can be the positive or the negative square root, but in both cases it will not matter because L of anything, we can look at L. L is 0. There is no x involved here, so no matter what I plug in L of anything, I will get 0. Therefore, the approximation of sine of 0.01 is 0. So we will now move to Taylor polynomials. Taylor polynomials are more general linearizations for polynomials of degree n, and you will understand this more with the examples. But first of all, let's talk about the notation. We write the Taylor polynomials t, and then with a subscript n of x. This is the nth degree Taylor polynomial. Basically, so if it's written T1x, this is the first degree, this is the second degree, this is the third degree. The higher the degree, the more accurate it is. So let's write what the Taylor polynomial is. So at x equals to a, the nth degree Taylor polynomial is f of a plus f, you put in a superscript 1 of a. This means this is the first derivative evaluated at a, and this times x minus a. Same for here. This is the second derivative evaluated at a. We multiply this by x minus a squared and we divide it by 2 factorial plus the third derivative evaluated at a divided by 3 factorial multiplied by x minus a cubed. And then this keeps on continuing until we get the nth derivative evaluated at a. We multiply it by x minus a to the power of n and we divide it by the factorial of n. Just a reminder of factorials. 0 factorial is 1. You just have to accept this for now. We will not really explain it. Now 1 factorial is 1. What is a factorial? It is if you multiply the number, let's say 2, by everything that's below it, the integers. So 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. This is basically what a factorial is. You can simply plug it into your calculator in order to avoid these calculations. And now let us move to an example. So the example is given f of x equals to cosine of x, find the third degree Taylor polynomial for f of x at x equals to 0 and use it to approximate cos of 0.2. So let us start. It's usually the way to start with Taylor polynomial questions. Always draw a table. And I will tell you what all of these things in the table are. But first, draw a table. On the top left corner, write n. And here they ask for the third degree Taylor polynomial. So make sure you have a 0, 1, 2, and 3. In the next row, this is the nth derivative of f. In the last row, this is the nth derivative of f evaluated at a. In our case, they told us they want x at x equals to 0. This means a equals to 0. So we evaluate it at 0. So note that if we're finding, let's say, the first derivative, we write it in here. So in this case, n equals to 1. However, when n equals to 0, the nth derivative, this is the function itself. So here we write cos of x itself. The derivative of cos of x is negative sine of x. And then the derivative of negative sine of x is negative cos of x. And then the derivative of negative cos of x is sine of x. And then we evaluate each one of these at x equals to 0. So cos of 0 is 1, negative sine of 0 is 0, negative cos of 0 is negative 1, and sine of 0 is 0. And now let's start finding the third degree Taylor polynomial. Don't forget here in the subscript you put 3 because it's a third degree Taylor polynomial. This is equal to f of 0 plus the first derivative evaluated at 0 times x minus 0 plus the second derivative evaluated at 0 divided by 2 factorial times x minus 0 squared plus the third derivative evaluate at 0 divided by 3 factorial times x minus 0 cubed. Now let's start replacing with f of 0. So f of x equals to cos of x. So f of 0 equals to cos of 0, which is 1. And this, we can here find it in the table. Now, the first derivative of f evaluated at 0. Let's look at the table. So it is right here. This is the first derivative of f evaluated at 0. So it is 0. So this entire term is 0. Plus, now we want the second derivative of f evaluated at 0. So again, let's look at the table. This is the second derivative of f evaluated at 0, and it is negative 1. And then we divide it by 2 factorial. 2 factorial is 2 times 1, which we can just write as 2. And then we multiply this by x minus 0 squared, which is x squared. Let's look now to the third derivative of f evaluated at 0, which we look at the table, it is 0. So this entire term is 0. So our answer is in fact 1 minus x squared over 2. Now we are asked to approximate cos of 0.2. So we were first looking at f of x equals to cos of x, and now we would like to approximate cos of 0.2. So as you can see, just look at them, x has to be equal to 0.2. So cos of 0.2 is approximately equal to the Taylor polynomial. Instead of x, we write 0.2. So instead of x, again, we write 0.2. So we get 1 minus 0.2 squared divided by 2, which is equal to 0.98 if you plug it in on the calculator. And this is our approximation. I just wanted to write a little note that when when we are centering it at 0 as we did up here, so in fact our a equals to 0, this is a special type of Taylor polynomial, and we call this the Maclaurin polynomial. Let us now move to another example about Taylor polynomials. So find the degree 3 or third degree Taylor polynomial for f of x equals to ln of 1 plus x at x equals to 1, and use it to approximate ln of 1.9. First of all, as usual, we draw the table. We want the third degree, so we reach in the table up to number 3. And then we put the nth derivative of f of x here, and we evaluated at 1 because they asked for x to be 1. So first, when it's 0, we write the function itself here. And ln of 1 plus 1 is ln of 2. The derivative of ln of 1 plus x is 1 divided by 1 plus x, and 1 divided by 1 plus 1 is half. The derivative of 1 divided by 1 plus x is negative 1 divided by x plus 1 squared. We evaluate it at 1 and we get negative 1 over 4. And the third derivative is 2 divided by x plus 1 cubed. We evaluate it at 1, we get 2 divided by 8, which is 1 divided by 4. And if you need extra practice or extra help regarding derivatives, feel free to check our other video about derivatives. And now let us find the third degree Taylor polynomial. So first write the equation and reach the third degree. So then let us plug in what we know. So f of 1, we can find this from our table, it's ln of 2. And then the first derivative evaluated at 1, it's half. We multiply this by x minus 1. And then the second derivative evaluated at 1, this is a negative quarter. And then the reason why I multiplied by half is because here we divide by 2 factorial. And what is 2 factorial? It is 2 times 1. So 2 in the denominator. And then we multiply this by x minus 1 all squared. And then here we have our last term. The third derivative evaluated at 1 is 1 quarter. And then we divide it by 3 factorial. What is a 3 factorial? It's 3 times 2 times 1, which is 6. This is why I wrote times 1 divided by 6. And then I multiply it by x minus 1 all cubed. And now don't forget that we are asked to approximate ln of 1.9. So our function is ln of 1 plus x. If I would like to approximate ln of 1.9, this means what's inside the lns has to be equal. So 1 plus x has to be equal to 1.9. So let us solve for x. X should be equal to 0.9. So then we will approximate when x equals to 0.9. So up we had the Taylor polynomial, which was the third degree Taylor polynomial. So instead of x, we now plug in 0.9. So let's do that. Anywhere we see an x, we plug in 0.9. So where is our first x? So first it's ln of 2 plus half times 0.9 minus 1 plus negative quarter times half times 0.9 minus 1 squared. I'm just writing it in a different color for you to be able to identify it quickly. Plus quarter times 1 over 6 times 0.9 minus 1 all cubed. And then write this on your calculator. What you will get is 0.64186. This is a rounded answer. And this is our approximation for ln of 1.9.